Hi, Zach.
Hello. Okay, there's already a fair amount of people here, so we can go ahead and we'll be able to find this recording. I am recording this, and it will be just on the announcements, I think. Um, Hello, everybody.
Like a school because I couldn't get
There's
my registration figured out, so I get it.
You told me about that.
Yeah.
Because you helped me with mine.
I think someone's unmuted. I think that's
Yeah. Alright, see you guys. Bye.
You guys are more than welcome to turn off your or turn on your cameras. I would appreciate that. If you did, you're not have to by any means.
He doesn't need to see this.
Unmute. Yep. Yes, I can. Cool. Um. Cool. So at any point, feel free to drop questions in the chat, or just feel free to just ask me out loud. A little background about myself. I am a fourth year here. I'm a double major in electrical engineering and math. This is my first year TAing, and I took this class a while ago, but I've been tutoring it for just about 3.5 or 4 years now. So hopefully I'll be able to answer any questions you guys have. So if at any point there are any questions, we can just go through some of the old assignments or material or the practice midterm or something like that. So if you guys have any conceptual questions, especially, this is like the time to ask. I don't know if there's any review. I know you guys have a lecture tomorrow, but yeah, feel free to ask away. And you can also just unmute yourself and ask a question if you have any.
Yeah, so let's say we're given a matrix that has more rows than columns, but each column
Okay.
is a pivot row.
More
Is that
rows than columns.
yes?
Okay, so tall matrix. What about it?
And so when there's a pivot in each column, does that correspond to a unique solution?
Say that one more time. When there's a pivot in every what, there's a unique solution.
If there's a pivot in every column, does that mean that there's a unique solution given
If
like
there's a pivot in every column, does that mean there's a unique solution? A pivot in every column, yes, so long as the system is consistent. So like if we have like say this is augmented, 1, 1, 1, like 0, obviously. um, okay, and we have just a bunch of zeros down here, or whatever. We can row reduce it to a form that looks like this. We'll either find that we're gonna have something that looks like this, or some kind of similar thing. But if it's inconsistent, no solution's done. Okay. Did that answer your question?
yes, thank you.
Yep. Okay. Any questions in the chat or any particular problem about any
So,
quiz or assignment or anything like that?
so for that one,
Mm-hmm.
say there was a on the right side, you see how there's three ones,
Yep.
and there was a two under there. Then what
Yep.
would be the result?
So if you have it like this, how it is written now, right?
Yes.
Okay. So if we have this system written like this, this is 0 times x1 plus 0 times x2 plus 0 times x3 equals 2, which can't be true. So that makes the system inconsistent, which basically there's a whole bunch of different inconsistencies, but for this, it's that 0 cannot equal 2.
There's no
So
solution.
no solution, exactly. So inconsistency in terms of solution set means you have a couple equations, and at some point, two of them have like the variable equal different things, so they can't exist in the same like set, if that makes sense. Okay, I'm getting a lot of questions about. Okay, one moment so I can scan through these. Span of columns versus span. So in a matrix, span of columns. Span of columns. I'm gonna kind of skip around some of these because some of these questions do seem rather similar. Span of columns. So I'm gonna write this in like vector notation. It's okay if you haven't seen this before. but essentially I'm going to write it like v1, v2, and v3. Where they're just our vectors, they're our columns, essentially, okay?
What? Excuse me?
Please mute yourselves. This is being recorded and sent to 1,300 people. So, it's okay if you have stupid questions. If you're yelling at somebody around the room, please try not to do that. Yeah, so these three vectors, essentially what span is it's the space that we can create by any combination of these three vectors. God, there are so many questions. This is being posted on Canvas. This will just be on an announcement. So these three vectors, what they span. So say like v1 equals like 1, 0, 0. Okay. v2 equals 0, 1, 0, and v3 equals 1, 1, 0. Okay. All right, so what is the span of these three vectors? So in like a three-dimensional space, come on, stupid, boop, boop, and this is our z-axis. You can think of it as I'm like literally like grabbing the origin and pulling a different line from it. So this is our z, x, y. Okay, so what do these vectors look like? This v1 looks like, whoa, oh, unit length of 1. And then v2 looks like this. This is just a graphical interpretation of it. And then v3, something like this, right? So essentially what the span is the combination of all of the different places where we can land with linear combinations of these two vectors, or of these three vectors in this case. So what are linear combinations? You can multiply by scalars for each individual vector, and you can combine them. You can add them. Technically, you can subtract them by multiplying them by another and then adding, but that's stuff that you don't really need to pay too much attention to. So the span of the columns creates a space, and then span of the solution set is where it gets a little tricky, and this is where everybody has all kinds of different questions. The best way to explain span of a solution set is how many ways can you get to B. For me, at least, this is how I tend to think about it. One of the wonderful or horrible things about linear algebra, depending on who you ask, is that there are a million ways to explain every single thing. So like say our solution set looks something like 2, 3. Okay. So what does the solution set look like? So we solve this in terms of variables, try to get a parametric form. We have x1 plus 0x2 plus 1x3 equals 2. And for the bottom one, we have 0x1 plus 1x2 plus 1x3 equals 3. From here, we solve for the lowest subscript, which essentially means the lowest like little number. So there's the 1 and there's the 2. They might not explicitly explain that, but that's what you're doing every time you do it. So x1 equals 2 minus x3, just by getting that to the other side. The other one, x2 equals 3 minus x3. And from here, we're going to put this into a parametric, or we're going to put this in a vector form. So we have our x vector, which is x1, x2, and x3, since we have 3 variables, because we have 3 different columns. Equals, and essentially all we're doing, x3 is free, so x3 equals x3. For like this equation here, basically to get it in our big like vector form, we basically just put a big vector thing around both sides.
Oh.
So here we have the vector 2, 3, minus x3, minus x3, x3. And here what we can do is we can break it up. So we're going to break it up into the points with x3, 2, 3, 0, and the points with x3, negative x3, negative x3, x3. Boom. From here, 2, 3, 0, plus x3, negative 1, negative 1, 1. So this is how you go back and forth between like them. So the span of this becomes the span of this shifted by this, which isn't a particularly great example, but for instance, if we set both of these equal to 0 from the start, so what would this look like? This would look like a line shifted by this. So this is our like line that's changing because it's in terms of x3, which is a free variable. And then our 2, 3, 0 is our shift. So essentially, like we have our line, negative 1, 1, negative 1, negative 1, 1, and then we're shifting it by 2 and 3, and it no longer hits the origin, but it's this big line for the solution set. So if we had like the 0, and we did this in last week's worksheet, I believe, where you did 2 examples, and one was like an augmented matrix equal to a number, and one was an augmented matrix equal to zeros. So find that you get all zeros when you like augment with the 0 to start here. And then essentially what this becomes is you get just the span of negative 1, negative 1, 1. Point negative 5, negative 5, 5. That is in the span because we can get from our vector, and this vector is negative 1, negative 1, 1, and it's combined one, but in this case it's just 1.
Someone needs to mute their mic. We can't really hear you.
You
Or
can't
I
hear
can
me?
rather. It's because someone's background noise is on.
Yeah, I just heard that as well. Can you guys hear me now? Better, I hope. With less
We didn't
background
hear
noise.
I didn't hear like half of what you just said after you circled it.
Okay, can you hear me like now as I'm speaking?
Yeah.
Okay. So say like we have, so how do we find if something is in the span? I'll answer that in a moment, and then I'll make my way through the practice midterm in a
I have
second
a
because
question.
I see a lot of questions about that. Yes.
So is the span of the solution set just the same thing as saying the span of like what we get like right out of like right here? This is the span of the solution set what you have, right?
This is the span of
What
the
you wrote?
solution set. Yes.
Oh,
What was
okay. I
the
just saw
first
it
part of that question?
I saw something different because can you get the span of a column set or a column or no?
Yeah, so like for here, the span of like the like span of this is 1, 0, 0, 1, 1, 1. Okay? But as we can see pretty clearly in this case, you can't always see that, is that 1, 1 is a combination of this one and this one. So we can simplify that as span 1, 0, 0, 1. Okay. Now going back to like the span of the solution set in this particular case, span of like this vector means anything that lies upon it. So if we had more than any linear combination of the two, in this case, it's just a scalar multiple. So if we had a vector like negative 5, negative 5, 5, that would be a solution to this question and would be in the span of the solution set. A lot of confusing terminology, but hopefully it's starting to make a little bit more sense to you.
So what you circled would be the answer to if a question asks what's the solution set?
Yeah, essentially, but I would leave it more in like terms like this. It depends on how they ask you to. They'll usually state like, leave it in this form.
So you're meaning parametric vector form or vector equation, etc.
Yes.
Right. Okay.
It'll be multiple choice, so we won't have a choice.
It's all multiple choice for y'all?
All but like maybe one of the questions.
Okay, noted.
What dimension would this be in? Would it be in R3?
The solution set would be in R3. The actual span of the thing itself would be in R2, which is very confusing to go back and forth, but you can think of solution set as like different ways we can combine our vectors. There's all kinds of different ways to think about it. I don't know how your particular professor explained it. Okay.
For the when you had like the solution set at the end there, if it
Mhm.
said what is the span of the solution set,
Yes.
if you're like if it was an inhomogeneous system and you did have like the added variables instead of just 0, 0, 0, would you include those? Or would you say like those variables plus the span, or would you just have like that simple span without the extra
Okay,
variables?
so hopefully they're not going to ask you a question like that because that is this is an aside. This isn't really related to linear algebra. Something is defined as linear in the technical mathematical definition so long as it passes through the origin. So as soon as you add like a vector or like something like in this case it was like 2, 3, 0, it becomes technically affine and it's not really as like comparable. So essentially like sorry, it's okay. So it was like you don't include both vectors because it's not like you can't combine your like scalar vector infinitely. It's just You add it once, and then everything is related, like comes off of that, if that makes sense. It's like our new origin.
Okay, so you would
So
write.
it wouldn't be in the span. It'd be like, I don't want to give you like a technical, like written anything, because I don't want to contradict your professor or anything that they have not said already.
Okay.
They shouldn't ask you anything that you haven't seen before, or that just seems very too far out of pocket. Why would the span of the columns be R2? Because essentially, the dimension of our span is how many rows we have. Because these vectors become 1, 0, 0, 1, and 1, 1, which are all two-dimensional vectors, so at most they can span R2. Because you have two variables, at most you can span two space.
How do you figure out the dimension of the solution set?
Dimension of the solution set is equal to the dimension. Sorry. The dimension of the solution set is equal to the amount of free variables you have. So if like we have 0 free variables, like we're gonna have a matrix that like we'll put it in reduced row echelon form, right? 1, 1, 1, and then I'm gonna write a big 0 just to fill in all the other entries as 0. This augmented with like 6, 40, and 10. What is the solution set? It's a singular point because there are no free variables. And what does R0 look like? What is something in the 0 dimension? A singular point. So you can think of like dimensions as like adding axes as you go up. So like R0 is a point, R1 you add a line, R2 you add a different line, and R3 you add one passing through it. At least to 3 space. Past that, geometrics become not as fun.
So would that one be in R3?
This one would be in R3, yes.
So how do you know if it's in like R3? Because I know if you have like a matrix X that's like a m by n, like row by column, isn't it like whatever the dimension of R should be is like n? Does that always hold or?
The dimensions of each vector in the span is n. So like this, if we have like say it's like a 5 by like 4, okay? What do our vectors look like? They look something like 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, so on. You'll have 4 of them. So with 4 vectors, the greatest space you can span is R4. But these are 5-dimensional vectors, if that makes sense. So this will create a 4-dimensional space in a 5th-dimensional space. So it'll create an R4 in R5. Does that answer your question?
Could you explain that part again? I was up with you until like you said it has like R4 and R5. Just explain that one more time.
Okay, so I'll just create a couple more. 0, 0, 0, 0, 1. Make it easy on myself. Okay, so how many vectors do we have here? We have 4 vectors, okay? So like think like breaking down from the very beginning. If we have 0 vectors, it's a 0 space. There's nothing. If we have 1 vector, at most it can create a line, right? Just geometrically thinking in this case. If we have 2 that aren't the same, they create a whole plane and create an R2. If we have 3, R3, 4, R4, and we can have up to 5. So like the best like simple example I can think is if we're in like R2, okay? If we have this vector here, 1, 0, right? This is a 2-dimensional vector, meaning it has like 2 different components, okay? What does the actual span look like? It looks like a 1-dimensional line. So on the graph of x1 and x2, this looks like this, right? So this is 1. And then what is this single vector? We can multiply by any amount, so it becomes this whole space. Even remember, we can multiply by -2, so it goes in both directions. This is essentially saying that 1 vector creates a line. If we have 4 vectors, they can create at most a 4 space, assuming that they're not linear combinations of each other. So does that make more sense now? So each of these vectors are in R4, but they're in R5 because they have 5 different elements. They have 5 different entries in R4, but they can at most span the amount of vectors you have. If you only have 1 vector, you can never create a plane, right? As much as I want to, like if this is my single vector, as much as I want, I can only multiply it. But if I have 2, I can multiply this one by 10 and this one by -1 and get this point in this plane that we're creating. Cool.
I have a quick question. Or somewhat quick, can you go back to the span stuff, like when you were doing it earlier with like this? I'm a little bit lost what you were doing. Can you explain it, please?
Yeah, I did already walk through this, so if you could like send me an email or something. I don't want to spend too much time on this. I only have an hour, so I'm going to try to move to a couple more questions in the chat, if that's okay.
By the way, someone double checked, and it's not all multiple choice. It's just no like right where you have to like write it and upload it.
Okay, yeah, thank you.
Did you say that
Go ahead.
Sorry, did you say that the 4 vectors could at most span a 4-plane or a 5-plane?
4.
Okay, thank you.
Yeah, so like if you think it down, the easiest way to think about it is think about like 2 or 3 space, right? You say you have like a 3-dimensional like box, right? And you have a single vector, you can create a line, R1. If you have 2, you can create at most R2. And this isn't saying that this necessarily can create R4, but it's at most R4. Okay.
Was another way of saying that like 4-plane in R5?
At most, yes.
Okay.
Plane is more of a 2-dimensional thing. It's like saying, can we have like a 4-dimensional line? Just say space, just for like transparency's sake. It's not like that I'm correcting you or anything, but that's like just the like technical term. Okay. So let me scan through some of the chat questions real quick before. One moment. Any tips for conceptual true false? Span of columns versus span. Okay. And if you guys could, if anyone can help explain some of the questions in the chat, please do that. There are 176 of you and 1 of me, so I am only so good. Let's see where this is being posted. I already said it's being posted. I'm going to send just an announcement with probably the link in a few hours. I've never recorded a Blue Jean session before.
I think a lot of us asked for number 11 on the midterm exam. Can we go over that?
Yeah, let me pull it up. And one thing I will say is, before we get into this, just to like help explain it, because I've had a lot of students come to me with this question. How to determine if you have 3 vectors. Like if we have like 3 vectors, like say we have something that's not as intuitive, like 4, 5, 6, 8, 15, 2, 1, 1, 1. Okay. How do we determine what this spans? Okay. So how we can also write this is if they give you a matrix A is equal to 4, 5, 6. I'm not putting this in this matrix for any reason. I'm just trying to show you that these are equivalent statements. 8, 15, 2, 1, 1, 1. So if they ask you what is the span of the columns of A or what is the span of A, it's the same as the span of these 3 vectors. But what we can find out is these vectors have to be totally like, they can't be like linear combinations of each other to create like, okay, I'm not trying not to trip myself in my words too much, but we need 3 vectors that are totally different that you can't get from combining others to make like a space. So like, I usually just work my way from like left to right, okay? So we have a vector. Cool, we have a line at least, right? That's the definition of a vector. We have a second one. Is this the same line? You should be able to tell pretty quickly. The only thing you can do with one singular vector is multiply it by a constant. No. So this is not. So 4 does become 8 by multiplying by 2, but when you multiply 5 by 2, you don't get 15. So the last question is this a combination of these 2? So essentially, do we have 2 vectors making up space, and the third one just is in that span and it's not really as important in terms of span, or do we have 3 vectors that create a whole 3 space? So how do we solve this? Rule of thumb, linear algebra, put it in a matrix. 5, 15, 6, 2. So if we put this in an augment with the first 2 vectors, augmented with the third one, what that is asking is if, like in general, as like a statement, it is equivalent to say, like, if I have an augmented matrix, this is asking, is this vector here in the span of this vector and this vector? Okay? So If it is, the system will be consistent. If it is not, the system will be inconsistent. Okay? This is also one of the worksheets, but I'm just going to go through it again. So we're going to put this in row reduced echelon form. Ooh. So just for time's sake, I'm just going to use a calculator for this. Reminder that you cannot use calculators on your exam tomorrow. And this would be a good exercise if you want to look at like row reduction stuff and like do it for yourself just to make sure you're able to do it. So when we put this matrix in reduced for echelon form, what are we going to get? We're going to get a 1, 0, 0, 0, 1, 0, and a 0, 0, 1. What does that mean? System is consistent, and that also means that B is not in the span of the columns of this side part. It's not A. But yeah, in A. Oops. Sorry, accidentally locked myself out of my iPad.
You said, oh, sorry. You said it was inconsistent, right?
Correct.
Okay.
Let's get my iPad back online. Very sorry for that.
If it's inconsistent, that means that the third vector isn't in the span of the first two, right?
Precisely. That is the definition of it.
Okay.
Yes, so exactly as someone said in the chat, we have three vectors. None of them are combinations of each other. If you've talked about linear independence at all, not in the exam, these three vectors are linearly independent. You have three vectors, so that you would write this as the span of 4, 5, 6, 8, 15, 2, 1, 1, 1. So that's the span of this, or the span of this. Equivalent statements. If we found this system to be consistent, then this span, it's redundant. We have an extra vector that's already in there. That's already included within the first two. So if this last one was all zeros, then the span would just be of the first two. Okay? Cool. All right. Let's
Wait,
look
for
at...
can I
Go
ask
ahead.
a question?
No, go ahead. Yeah.
For that one, if you were to set AX equals B, could you quickly explain where B lives and where X lives?
Yeah. Not capital B. We're doing a lowercase b as a vector. Okay, so one of the things to note that I know has been a little patchy for some of the different classes and stuff. Let's say A is an n by n matrix, okay? And
do
M matrix multiplication.
Do M by N.
M by N. Okay, that's fine. M by N makes it a little easier, more general.
That's
okay?
just the way it was in the textbook.
Okay, yeah, I understand. Okay, so to multiply x, so we know x is a column vector, so it's by 1. So we know it's an n by 1, okay? So to multiply matrices, the way I like to do it is I like to write my dimensions of each one right next to each other, okay? And then I draw a little box around the middle part, and my resultant will be an m by, nope, stupid, m by 1. Just drop each individual part down, okay? So B is an m by 1, or it exists in the same amount of, it has the same amount of rows, and it's a column vector. So the original question was if this is our matrix A, where does like X live and where does B live? So X exists as you can think of it as like a variable vector, okay? So it's like x1, x2, x3, ... to xn in this case, where n is the number of variables and it's also the amount of columns in our matrix. Okay, that's X. B is an m by 1. B, there's a bunch of different ways you can interpret B. I'm going to get to number 11 on the midterm in a moment. I'm sorry, I promise I'm getting there. It's an m. So B is an m by 1. Essentially, B lives inside the span of A, of the columns of A, so long as like when you reduce that, it's consistent. X doesn't really like live anywhere. It lives in like n space because there's n dimensions. So this is in Rn because it's an n-dimensional vector, right? Pretty straightforward with that. Just like how many variables you have is how many like the dimension you're in or the space you're in. Okay. Did that answer your question, I hope?
Yeah. Perfect. Thank you.
Perfect. Okay, cool. All right, let's look at
Can we
this
do
simple
number
midterm.
11 now?
Yeah, I'm getting there.
Okay. Yeah, sorry. It's
No,
really-
I understand. I'm getting there. Alrighty. Okay, so I assume what I'm seeing is the same thing that all you were seeing, but I'm not going to share my computer. So I'll just write it on. I don't know where I can go. Do this. No. Oh, there. Okay, that is like the worst place it could have put it, but like, okay. Okay, so is this the question that everybody sees for this one? Yes. Any confirmation whatsoever?
Yes.
Okay, cool. Okay, suppose A is a 3 by 4 matrix. Which of the following can be the solution set to the equation AX equals 0? Okay, so A equals 4 by 3. Boom. Set up, start. Fantastic. Okay, so there's a lot of different like terms to learn with linear algebra. One of the big things is can be the solution set, okay? To the equation AX equals 0. We'll get to that one in a minute, but that's also very important. Okay, so what does this mean if A is 4 by 3, what does that mean for X? Or how many unknowns do we have? It means we have 3. Yes, very good. So our solutions, so this is AX, it'll look like this, x1, x2, x3, 1 by 3, okay? They're at the same height. I'm just a bad artist. I'm an engineer. I'm sorry. Cool. So, the first thing that I would say we could do B first, because B is a little bit more trivial. Can the solution set, so what dimension is this vector? This is in R4, right? So what does that mean for our solution set? It means we're talking about 4 different variables. But how many variables do we have? We have 3. So you can tell immediately, gone. Okay, false.
I don't understand how you did that.
Okay, so our solution set is at most what dimension? So how we get that is it's at most the dimension of our variables, okay? So we have x1, x2, x3. That makes solution set at most R3, okay? Because we have 3 unknowns in the solution set, which means we're going to have most in R3, or a 3-dimensional space.
I answered that on the test, and it said it was incorrect. It said that
false?
It said that it could be the set of solutions to AX equals 0. And I was very confused.
Let me double check on this.
No, it was false.
Okay, I was like...
Yeah.
It's false.
Where to go?
Okay, then I think mine is broken. That's really weird.
Yeah, I would email your professor about that one with like a screenshot that whatever, just to like confirm. But
all right, thanks.
Yes, that is okay. All right. So does this part make sense so far? Are there any questions about this? And another thing to note, I promise whatever questions you may have, I have asked stupider questions in front of more people. Feel free to make as many like mistakes or ask dumb questions, because I promise if you're thinking it, somebody else is thinking it as well.
Is the solution? Sorry.
Go ahead. No, go ahead.
Sorry. Is the solution set the dimension for the solution set given by the number of columns?
The dimension of the solution set given by the number of columns? Yes, because the number of columns is equal to the number of like variables we have. The number of variables is the amount that we have in our solution set.
Wait,
so,
there's like a terminology thing that's going on. When people are saying dimension of the solution set, Like there are two of them, right? Because like there can be like, okay, does the solution set lie on a plane or on a line?
Yeah,
Like
so
is
the
that
dimension of the
dimension?
solution set, I'm talking about it in terms of at most, right? Because you have
Okay.
x1, x2, x3. The
So like
actual, like,
R.
what it spans, what it creates is different than, like, just the space it exists in, which is what I'm talking about right now.
Got it.
Sorry if that's a little confusing. And then span of, like, a normal matrix A is totally different. Um, Not, like, necessarily, they're, like, relate to each other, but not in such a way that you need to, like, focus on that.
Just to reiterate, so the number of free variables is like the dimension of the actual solution set, but then the number of columns would be like the maximum like dimension, right? Whatever the
That is
R
correct.
n number. Okay.
Because think if
Thank
you
you.
have an all zeros matrix, right? You have all columns of zeros. How many variables do you have? You have the same amount of columns as you do variables. But they're all free, right? So they can be whatever they want. So you just keep adding axes, you keep adding dimension, and it creates that whole space. So that's what it is at most.
Got it.
Not really gonna see that ever, but I'm just talking like in terms of like what to think about. Because in this instance for like B, do the number of rows affect R dimensions? Yes, they affect the dimension of the span. So that's the difference between like span and solution set. That's like the dimensionality of like the difference there. So like for this solution set, it exists at most in R3. It exists in R3, but it's probably like a line or something. A line, a plane, or at 0 or something like that.
You've described both like at different times, but can you explicitly like compare how to find the span of the columns versus the span of the solution set? Because like one
Yeah.
way you have to look at columns, another way you have to look at rows, and it gets really backward. And I've seen like a
Yeah.
lot of questions
I'll do that in
definitely.
a moment after I make my way through the rest of this question.
Thank you.
The set of all vectors of the form 1, 0, 0 plus x2, 2, 1, 0, where x2 is any real number. Okay. So this is the part where it helps to think a little bit more geometrically. So what does this mean, right? Question, like base question of any like thing you're being asked, right? You have a constant vector plus your free variable times a vector itself as well, okay? What that means is if you just have like x2, 2, 1, 0, starts at 0, right? Because x2 can be 0. Well, I'll write it like this just so y'all can see it as well. So for this particular form, we write it as like x1, x2, x3 equals 1, 0, 0 plus x2, 2, 1, 0. Okay, this is the definition of like this like form. Okay, we get it from parametric form. This is our like vector form. Okay, so here, what does this space look like? So we have some vector right here, multiplied by, I'll zoom in over here for right now, multiplied by some number, some real number, okay? So what does this create? We have a vector multiplied by any real number. It becomes, just like centered at the origin, a line, right? And from the like big takeaway is like you have this constant here. And this constant is what kind of screws everything up. Because the solution set to the can be the solution set to the equation ax equals 0. Okay? For ax to equal 0, it has to be true that like the solution set is like you have the 0 in there. So like can this ever be 0, 0, 0? No, because we have 1, 0, 0 just existing permanently. And regardless of how we try to combine the second vector times x2, we're always going to have something left. Because even if we cancel out like this top number, this 1 and this 2, then we're left with the remainder here. So that's like the terminal, like the geometric approach to it.
So just to summarize, that basically means anytime it's like non-homogeneous, it doesn't include, like the solution set does not include the 0 vector. Is that like another way to put that?
I believe so, yes.
Okay. I think that's question 1 too.
All right, are there any like large questions that people are seeing in the chat that people want to go over?
Could you go over number one?
Number one?
Yes.
Okay, cool. Number one. True or false? This one is a little tricky. It's one of like the special cases. They love to throw you these. It just you have to kind of like think about like all of the different things going on. So, true or false? Okay. A. You have two matrices. Well, if two matrices have same row reduced echelon form, then the spans of their columns must be equal. They have the same reduced row echelon form. The span of their columns must be equal. So did anybody find like an easy solution to this?
I did.
Okay.
So if you have like a 2x2 vector that's like 1, 0, and like so the first row is just 1, 0, and the second row is 0, 0. And then if you have another vector that is 0, 0 as the first row and then 1, 0 as the second row, in RREF they should be the same. Like they should have the same RREF, but they're completely different in terms of their spans. That makes sense.
Yeah, could you say those vectors again?
Epsilon form. We row reduces, that's their spans.
So if you have so two 2x2 matrices, right? So the first one is like, I don't know. Can I draw it on here or?
No.
Okay. So like if you have, it's easier to like see it visually, but like if you have like the first row just be 1, 0 and the second row be 0, 0. Yep. And you have another 2x2 that's the first row is 0, 0 and the second row is 1, 0. Or wait, I'm going by rows, so it's like
the rows. My bad. Yeah.
Yeah, exactly. So if you reduce it to RREF, they have the same RREF, but they're two completely different vectors because this would be like, I think the first one would be like on the X axis and the second one would be on the Y axis. So they're completely different spans.
Okay. Yeah, that makes a lot of sense. The explanation I had was a little bit more complicated than that, so I'm glad that someone else found a more simpler solution. So,
Can you draw and show us like what you're saying?
Say that again?
I'm still a little bit confused. Can you reiterate that again one more time?
Yeah, so essentially, like, I'll make it even simpler than this. Like, say I have like a simple like 2x1, right? Like, say I have the matrix like 0, 1, right? What does this look like in RREF? Reduced row echelon form. One of the rules: all the zeros to the bottom. So we switch them, right? Now, say we also have the matrix 1, 0, okay? It's already in reduced row echelon form, right? But you see that like the vector 0, 1 and the vector 1, 0, like they're totally separate, right? They have totally separate spans.
But their spans are their spans would be 0, 1 and then 1, 0. Oh, never mind. Yeah.
Yeah, so like if like we're plotting these spans, boop, 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 boop. Like here's our 1, 0, and here's our 0, 1. Totally different spans, right? But they have the same reduced row echelon form.
Then how can we swap like the rows of matrices if they have completely different spans? Like why is that a property that we can do that if we're making new matrices?
That is a much more complicated question than I think you might have Hoped for. Basically, when we do row operations, when we're doing like row operations, we're typically talking about like equations or different kinds of like spaces and stuff like that. But for like the physical, like I don't want to tell you, don't worry about it because I hate that answer. It does always refer to your span in the initial form. Don't do any manipulation because that changes the span. That's essentially what this is supposed to show. Okay. Like just because a matrix can be put in row reduced echelon form doesn't mean it is in row reduced echelon form to start, or just because like these span this doesn't mean they always do. This essentially, like when you do these row operations, you're finding the solution set. Like you're finding that instead of the span. That's like the big like contrast between the two.
Okay, I think I understand. I think I was overthinking it. Thank you.
Yeah, I totally understand. All good.
This might be a bit of a dumb question, but typically when we have a matrix, doesn't each column represent a variable? But why then, when we're trying to graphically plot it, does one row represent the x axis and one row represent the y axis?
Okay, so this is the difference between like the stuff you started with, like your actual like equations and stuff, and then your actual like vector stuff. So one of the most wonderful things about linear algebra to me, you take some kind of math, some kind of problem where you're stuck, and you put it in linear algebra, and you screw around with it for a little bit, and then you spit it out. And that's kind of like the point, is you can put different things in, and they have different like meanings in terms of like what you're doing with them. Okay, I see the request for number 19. I'll get there in a minute, okay? Yeah, so that's the question of like span, which is when we're thinking of like spaces, and solution set, which is when we're thinking of like solution like areas and stuff. Does that kind of make a little bit more sense? I hope. They're just like separate is essentially what the like answer is, I guess.
When we're dealing with equations versus with vectors, it's unrelated. So the equations columns is variables, but with vectors, it's not necessarily.
Yeah, I wouldn't say unrelated, but mostly unrelated. All right, so let's get to question 19. We had 15-ish minutes left. I'll try to stay a little bit over, but I have some things I have to do tonight, unfortunately. Okay, so 19. Write a matrix A. A equals A, B, C, D. Okay, satisfies both the following properties. Span of columns. Is the line x1 equals 2x2. Okay? And so this is 1. And for 2, the set of solutions to the equation. So set of solutions to ax equals b is span 3, 1. All right, so you can start at either one of these points. Essentially, this is like trying to connect the different things together. So the span of the columns, if you have a singular line, what does that mean? It means we only have one base vector. That means the other column is a linear combination, or in this case, just a scalar multiple of the other. So what does that line look like? So x1 equals 2x2. We'll call this x1, call this x2. Like that, right? That's crossing through 0. So for every like 2 and 1. Okay. Rule of thumb for me. If you have a different rule of thumb, that's okay. Think of the simplest solution. So what vector spans this? Okay, 2, 1, right? 2, 1. Okay. That's the span of our columns. So what that means is the second column is some other kind of linear combination that satisfies like 2. I'll make some different variable. I'll call it, I don't know, h. 1h. Okay. So it says a is 2 by 2. So we can call A and C 2 and 1. Okay. Now for the second part of the equation, this is dealing with rows instead of columns. So the set of solutions to the equation AX equals 0 is the span 3, 1. Okay, what does that mean? It means if the set of solutions to AX equals, not B, 0. My bad, that is rather important. What does this mean? This means our X is equal to X1, X2. This is just like the definition of what the X vector is. Equals. So to get from span 3, 1 back, 3, 1, X2, because we're not going to have a span in terms of X1 for a solution set. Okay, so they just worded this a little poorly, I would say. Span of the columns is the line X1, X2. Column whatever variables want. Column like alpha 1, alpha 2. They're different than this X1 and X2 now. So I'll call them something different. I'll call them A1 and A2. Okay? Let's make this A vector. Okay? Okay, so from here we have A1 equals 3A2 and A2 equals A2 because it's free, right? So from here, what we can do is we can multiply this in by the distributive property, 3A2, A2. That's how I got from here to here. Essentially, I just took the like vector notation off. Okay, so we have something that looks like this. A2 is A2. We don't really have to worry about it. A1 equals 3A2. So for like this first row here, we have A1 is 2. So we have 2 equals 3A2. So what does A2 equal? A2 equals 2/3. Okay. So this 2H and 1H just has to be the relation between the two. So like this one is 2/3. So for it to still match this like column, like the span itself, right? This top one has to be this bottom one times 2. Okay. So from there, I hope you can divide 2/3 by 2. It's 1/3. This is a possible solution. There's no like one solution. Because you can multiply, like, you can create all kinds of different combinations of this, because I picked 2, 1. And then I went from there. So does this make more sense now?
I have a question.
Yeah.
So you can pick any numbers, like for 2 and 1, you can just pick any numbers, or did it have to be 2 and 1?
It had to be any number such that it satisfied this first condition here. The span of the columns is the line x1 equals 2x2. Okay. So we could have picked like 1,000,000 and 500 billion, or pi over 2, so long as it satisfies like this condition that x1 equals 2x2.
So when it talks about the span on point number 2 there, it says the span is 3, 1. Is that sufficient? Can you say that then like x1 equals 3x2 and x2 equals x2? Like, is that where that comes from?
Yes.
In like the parametric form. So like if you have that, wouldn't the like number in the second column there, or like where your arrow is, wouldn't those need to be negative values when you move it back over like when you move it back over left, like if you have like equal signs? You know what I'm saying? Like you have
Yeah,
like the
no, you're right. Yeah.
Okay.
Wait, I don't think this is right because it doesn't fit the second condition, this solution.
Yeah, I think I missed a negative or something.
Because when you got the A1 equals 3A2, aren't you supposed to do like A1, like aren't you supposed to put it back, so like A1 minus 3A2 equals 0, like that form?
So writing it like this, since it's like equal to 0, this is the same thing as saying a1 minus 3a2 equals 0. Okay. So like we could solve like this as well, and we'll get that like if we plug in a1 is 2, we'll still get a2 is 2/3, right? And we'll get a2 minus a2 is also equal to 0. Because if we had like a b, think back to that worksheet problem. When we had like a b that was non-zero, we had that extra constant vector.
Where did you get that A1 is equal to 2?
A1 is equal to 2. Oh, because we have it right here. Right here. So this A1 and A2, think of this as like A1, A2. Or rather, these are our A1s and these are our A2s because we're in our solution set now. So we could have done the 1 as well, right? We could have done 1 equals 3a2. So I'm talking about the a2 right here now. For 2 equals 3a2, that's talking about this one here. It gets a little tricky with all these different variables going on, but it just, if you have a different numbering system, just keep it consistent, keep it kind of similar to how the professor does it. Okay, did that hopefully answer that question?
Yeah, can you do 18 if possible?
8. Okay, are there any large conceptual questions that anyone has questions out before I do another example? Having more rows than columns means for a span and solution set. I did go over that a little bit earlier. More rows than columns means, yeah, you'll be able to see the recording of the session. If you have more rows than columns, that means a handful of things. It means the dimension of your vectors is higher than the dimension of your solution set. It means you have more equations than variables. It means just like a handful of things like that. If you wanted to watch the recording, hopefully that'll answer your question. Okay, so we'll go over 18 very quickly. Oof. Okay, so A is 3 by 4, 3 by 4. And B is some vector such that the solution set for the matrix equation Ax equals B is the parametric vector form 4, 0, 1, 0. Okay. So we have x1, x2, x3, x4, because we have our 4. We have 4 unknowns. Okay. So I'm just going to go ahead and mash all of these together. So we're going to get 0x2 minus 4x4 plus 4 x2, 0x2, 0x2 plus 0x4 minus 2x4 plus x4 plus 0 plus 1 plus 0. This is a vector, okay? This also gives us a fantastic set of equations. x1 equals negative 4x4 plus 4. x2 equals x2. x3 equals, what's that, negative 2x4 plus 1. And x4 equals x4. Cool. So what do we know? x2 and x4 are free. Just as like as a basis, right? x2 equals x2, x4 equals x4. Check. That's like a good like sanity check. So moving forward, the solution set is this. Okay. So coming from here, we're going to create x1 plus 4x4 equals 4. Since we have x2 as like a free variable and x4 is a free variable, there's not going to be a pivot in their columns. So we know we're going to have a 1 here, double zeros here, or sorry, they're there at least. Yeah, actually. Okay. And then I'll rewrite this one as well. Sorry if I'm kind of all over the place. Okay. it's what? 1, 2, 0, 1 equals 4, 1. Okay. So we don't have any other equations, so I just fill in the bottom of the row zeros. The way I would do this is I would just do it by hand multiplication. How do you multiply a matrix and a vector? 1, 0, 0, 1. This is the way I like to do it. Your professor might have taught you something different, but I'm going to explain it the way that I do it.
Why is it 1001 instead of 1004?
Oh, because I can't write. That's why. My bad. Okay. Multiplied by the vector. 4, 0, 1, 0. Okay, first we check if we can multiply. This is 3 by 4 times a 4 by 1. I'm draw my little box. Check. Yields a 3 by 1. Okay. So I don't have to write this again. Copy. Over here. So I'm just going to show you how to do matrix multiplication. I'm not going to like work all of the things out. So this is going to be a 3 by 1. So the way I like to do this is I like to raise the second part, and then this one down here is my answer. Okay. So the way I do it is I build my little bridges. And for the first one, it's going to be like 1 times 4 plus 0 times 0 plus 0 times 1 plus 0 times 4 plus 0. And then you fill in for the rest of them. Okay, we're getting a little close to time, so if there's any other particular question anybody has, feel free to ask that as well.
That 3 times 1 thing that you just did, can you show it again real quick?
Yeah,
just want to
absolutely.
clarify.
So when we have like our two matrices, right? So this is, we multiply like to get a product, right? So we're going to have whatever, like, to do it, you multiply this by this, plus this times this, plus this times this, plus this one times this one, and the sum goes there, right?
Yeah, I just want to know that you put the 3 and the 1 together, and that's going to be your final answer, like
Correct.
format.
That's going to be the dimension of my final answer. Yes. Yeah. So essentially, how that works is, like, here's a better place to see it. We have 1, 2, 3 going this way, and 1 going this way, and they combine to get a 3 by 1.
Got it. Okay, thanks.
Anybody have any more questions? I hope the chat, I see that people are answering a lot of questions in the chat, so hopefully that's been...
Can you go over number 10?
Number 10, sure. I did see that one a couple times. Ban of UVW. Okay. Yeah. So this is one of like the, this is like a very important, like being able to tell span. So I assume you guys have talked about linear independence. I'm not going to make your exam. I'm not going to think in terms of it. I'm not going to explain this in terms of it. But essentially what this is asking is how many different, like totally separate vectors do we have? Okay. So the first one, -1, 1, 2. Okay. So I always start from left to right. So I have a vector. So what does that make it? R1 at least. Okay. So I have a second vector. Okay. 0, 2, -1. Okay. Okay. Is this vector here a linear combination of this first one? What is a linear combination? It's take all of your like things that you already have and multiply each of them by some constant and add them and see if you can get this. Can you? In this case, the only thing you can do is multiply by a constant. So, question 1, can you get from 1 to 0? Sure, multiply by 0. Can you get from -1 to 2 by multiplying by 0? No. So you have at least 2 different vectors now, okay? So now we have a plane. Because we have 2 different vectors that are not scalar multiples of each other. So the separate vectors creating a plane. Okay. How do we find out if the third vector is in term, like is the third vector in the span of the first 2, or is it totally separate? How we can do that is we solve an augmented matrix, because that is the definition of it in terms of a like vector. Okay. So what we're going to solve for is we're going to solve for what times this one plus what times this one gets negative 1, negative 1, negative 1. And if the system is inconsistent, that means that it can't happen, right? So just to write this out, let's do some vector multiplication. So we can distribute this in, we can distribute this in. So we get a, negative a, and 2a, plus 0, 2b, negative b, right? Equals negative 1, negative 1, negative 1. Okay? Cool. From here, we can get some equations. A, negative 1. Negative a plus 2b, negative 1. Okay. 2a minus b is negative 1. Okay, this is 0. So does this, like, are you seeing how we flow from like our vectors to see if it's in the span now? Because if we can combine these in such a way that we can get this result, we'll be able to see if it's in the span or not. So after row reducing this, we're going to take out a couple of things. We're going to write this like ax equals b. So this is 1, 0, negative 1, 2, 2, negative 1. Multiplied by our variables, a and b, equals negative 1, negative 1, negative 1. Okay? And this should be very familiar to you at this point. 1, 0, negative 1, 2, 2, negative 1, augment, negative 1, negative 1, negative 1. So this first one is equal to, like, a is equal to negative 1. So you row reduce it from there, and you'll find that a and b are distinct, and the system is, you can get a solution for a and b, and the system is consistent. So that means that W is in the span of u and v. So you have two different vectors creating a span that creates a plane. But we have our 1, negative 1, negative 2 for our vectors. These are three-dimensional vectors. Okay? So you know it's in R3. And you know based on the span, so this is span of 1, negative 1, 2, 0, 2, negative 1. This is our span. These two create an R2 in R3 because they're three-dimensional vectors. Okay.
Does that mean that they make a plane in R3?
Wait, is it R3 or R2?
This creates an R2, which is a plane, in R3.
And that would be the span of the columns, right?
Read the span of the columns, correct.
Okay.
Yeah, it gave us vectors to start, so we can
I have
take
a
that.
question about this. So when you went from the augmented matrix to the span, why did the negative ones as the b as the augmented column disappear?
Oh, because I skipped a step because I was being lazy. So essentially you're going to solve this and you're going to get like a 1, 0, 0, 1, 0, 0, augment negative 1, and I don't know, 1, right? No. What? Negative 1 times negative 1 is 1. Also negative 1? I don't know. That looks about right. So you're going to get something that looks like this, right? This here. Okay? So let's look at this. What does this mean? Is the system consistent? Check. Fantastic. By definition, if you can augment like your vectors, augmented with another vector b, that by definition means b is in the span of the columns of the other ones. Okay? From that, we determine that this third vector is in the span of the first two, so we don't need to worry anymore. We just have to write. So now we know the span is two different vectors because the third one is encompassed in that. Two different vectors create R2. There are three variables within this, within each vector, R3. Plane in three-dimensional space. How do I get a plane in R3? Yeah, so say I'm existing in R3, as most of us do. They have a piece of paper, infinitely flat. You have a plane, fantastic. that's like the best example of how to think of it like that. Once we get to higher dimensions, stops working as well. In terms of like thinking about it. So we're not getting R2 in R3. I'm writing it as an R2 or a plane in R3, if that makes sense. Okay. I saw a lot of questions for 18. Does A equals B? For B, you could solve that and determine yes or no. For number 18 is what I'm on right now. And for A, does A times that equals B? So what is B? B is, where the hell did I write it? Where was it? Oh, it's this one. Equals B. Well, we can find B just with, with this like augment. So this is our like B, 410. So if it yields that, yes. If it doesn't, no. I think it did, right? 4, 0, 0, 1, all zeros, 0. Yes, it does. Okay, where are you going to post the video? I'm going to post it on the announcements on Canvas.
Can you go over 15 real quick? It's simple, but I don't understand it.
Absolutely. I do have to leave rather soon, though. But suppose we're asked to find one solution to a consistent system of 5 linear equations in 4 unknowns. Okay, linear equations and unknowns. What does that mean? It means we have a 5 by 9. Okay, because this is our x vector, and this is a 5 by 9, and our x has to be a column, so it's by 1, the same number of columns. Okay, so right here we have 9 different like variables in play. So a consistent system of 5 linear equations and 9 unknowns. What does this correspond to? Okay, well, what does our vector exist in? So here are all of our like 9 vectors, right? Okay, so how many entries does each one have? It has up to 5 entries. So for like just this first one, we'll call it like A1, A2, A3, A4, A5. So this vector, does it span 9 space? No. Does it span 8, 7, 6? No. You have 5 within this vector. Okay. Yes. Find one solution. Sorry, I'm just trying to like triple read everything so I don't accidentally tell you something totally wrong. Yeah, a linear combination of 9 vectors, because we have these, like this vector x looks like a big like x1, x2, all the way to x9, okay? And what this is also saying is like we have like x1 times our first vector, a1, a2, a3, a4, a5, plus whatever follows like x2, b1, from that, yeah, so we have our vectors which are all 5-dimensional, and we have 9 different vectors. So unfortunately, we are a little over time. If you guys have any more questions, please email me, message me on Canvas, message any of your TAs. So yeah, send me an email. Yes, I remember no recitation on Friday. So best of luck to all of you. I'll see some of you in the proctored session tomorrow. But cool.
Thank you very much.